Hello everyone, I am Meghamala from Electronics and Communication Department, working as an assistant professor in IARE, Dundigal. So, welcome to the presentation, and today's topic is all about the implicit continuous assignment. So, before going to the topic, let's recollect what we have discussed in the previous previous class. So, this implicit continuous assignment So basically, coming to the point, implicit continuous assignment is nothing but in the data flow modeling, we have seen what is explicit continuous assignment, what is a continuous assignment, and what sort of keywords that we have discussed in the continuous assignment statement. And coming to the implicit continuous assignment, we see here the data flow modeling, it makes use of the functions which defines the working of the circuit instead of its gate structures. So, here in this, the very first statement is talking about the data flow modeling. In the data flow modeling, we see the continuous assignment statements. We see the statements based on the data flow, but not in terms of the gates, okay? But not in terms of the gates. That is, the working of circuit could not be seen in terms of gate structure, but we see the mechanism and everything will be done by using the data flow modeling. And the second point is here, the data flow modeling uses several operators. As we know, different operators we have discussed, like lexical tokens that we have discussed in the previous class. So here the data flow modeling, it uses several operators and it acts as an operand to produce the desired results. So in order to produce the desired results, the Verilog is having the data flow modeling. It uses the several operators. The data flow model, it uses several operators in order to acquire the desired output. And coming to this, the Verilog already, it has a library of several operators or the lexical tokens. We see the Verilog provides about 30 operator types. So the gate level modeling, basically the mechanism, it deals with the data which transfer from the one block to the other block or else from the one net to the other net, and that data flow model, it has some operators. So in Verilog, we see it provides the 30 operator types. Okay, around 30 operator types we could see in this Verilog. And the data flow modeling styles is mainly used to describe the combinational circuits. So only in the combinational circuits, but not in the sequential circuits. Only in the combinational circuits we see the data flow modeling, which is the different styles in the data flow modeling can be seen only to describe the combinational circuits. And coming to the last point, the primary mechanism used is a continuous statement. As it is an implicit continuous statement, the primarily we see the mechanism is all about based on the continuous statement, whether it could be explicit or implicit, but basically the main statement that we see here is continuous assignment statement. So what is this continuous assignment? This is a value is assigned to a data type called net. We all know what is a net. Net consists of the vectors and as well as a scalar variables or the values, which is used to represent a physical connection between circuit element in a continuous statement. So in this continuous statement, we see there is a physical connection between the circuit. There is a physical connection between the blocks. So in the previous session, we have discussed if this is a circuit, complex design circuit, complex digital circuit. This complex digital circuit is comprised of various blocks. So we see there is a connection between block 1 to block 2 and so on. Okay, this is nothing but a net. So here it says that there is a physical connection between the circuit element and that you calling it as a net. Next, the value assigned to the net is specified by an expression that uses operands and operators. So here for this particular net, we specify an operator or else the operand. Operators could be of logical operators, okay, bitwise operators and so on, whereas operands are nothing but the variables that you are considering. For example, if you are considering a AND gate, you see A and B are the input and Y is the output. So Y is nothing but A dot B. So here A and B are the inputs, A and B are the operands, Y is the output, A, B, Y and are nothing but the operands, and the operator that you are using is AND operator. Okay. Next, the data flow modeling styles is mainly used to describe the combinational circuit. As we discussed earlier, it only describes for the combinational circuits but not for the sequential circuits. Why the combinational circuits? Combinational circuits because we see combinational circuits is nothing but it's a complex of more than one or the two devices circuited connected in a particular net. So the primary mechanism used is a continuous statement, and the continuous statement, it replaces the gates in the circuit description and describes the circuit at higher level of abstraction. So here in the continuous assignment, you see there is a replacement of the gate. Why? Because this implicit continuous assignment, that is a continuous assignment, this mechanism is being seen only in the data flow modeling but not in the gate level modeling. So such that wherever we find the gates in the procedure, we see that this continuous assignment statement has a capability to replace it with a gate in the circuit. A continuous assignment statement starts with a keyword assign. So as we see in the syntax, we see this continuous assignment in the syntax, it starts with a keyword assign. So here goes the syntax. The syntax says that the syntax of continuous assignment statement is assign. Assign is a basic keyword that we have to represent first, and here we see some delay in the left hand side of the net, which is equals to right hand side of the expression. So to the left hand side, we are representing with the assigning word keyword, assign word keyword with some delay. The delay could be 3:0 or 5:0. So if it is 3:0, that means what? It is a 4-bit of delay. If it is 5:0, it is a 6-bit of delay. So the right hand side is nothing but the expression, that is the output that is output which obtaining from the circuit that you have considered. So LHS net is a destination of net of one or more bit. LHS contains the net of one or more bit. As I said you, here it is a 4-bit of delay we observed, right? So the left hand side always consists of, it's a net of one or more bit, whereas the right hand side expression is an expression of various operators. So here you see the various operators. If it is an AND gate, you see AND, or, isn't it? Not. So the right hand side expression consists of a expression with respect to the variable operators. The left hand side consists of the bits, one or more number of bits. The statement is evaluated at any time of the source operand, value changes, and the result assigned destination after the delay unit. So here you see the statement is evaluated. The given statement, the continuous statement will be evaluated any of the source operand if the value changes, and that will be assigned to the destination later on. Okay, after sorting out with the delays, that will be stored, or else the result will be assigned in the destination with the right presentation of the delay, with how much of delay the input is carried out and with how much of delay the output we got. Okay, so these are this sort of changes that you will see from the left hand side and from the right hand side. So here in the example given, assign out1. Assign is a keyword for this continuous statement. Out1 is equals to in1 and in2. So perform the function of both inputs and assign the result to out. So my output is 1. So I am performing both in1 and in2. I am storing the result in the out. Similarly, assign out, this is for not in. So this is for in1 and in2, and I am placing the output at output 1. Whereas here for this output 2, what I am doing is not in. So this is a not in, this is an input, and this is the output. So the assign with #2. #2 is nothing but it is a delay with a delay of 2 nanoseconds. So A bar, and B bar and enable. So this is to perform the desired function and assign the result to units. So here the result that we observed, the delay is of 2, and we are assigning for the given operation, that is out1 and out2. For 2 different operation, we got the delay as 2, and we are assigning it with the delay of 2. And the target in the continuous assignment expression can be of the following. So what are the targets that we see here? Basically, it must be a scalar net, it could be a vector net, and the constant bit select of a vector, or else constant part select of a vector. A part can be sorted out and can be selected. Okay. And the concatenation of any of the above. So you can take a part, or else you can select a bit, and you can concatenate both. Next, example in which scalars and vectors are declared and used. So how the scalars and vector nets are declared and how they are used. This is an example we can see here. Wire count Cin, that is scalar net declaration, and wire 3:0 sum AB vector net declaration, and assign count sum, the concatenation A plus B plus C in A and B vectors are added within C in. So basically in this example you have to remember one thing is scalar and the vector net declaration. What are the scalar net declaration and what are this vector net declaration? Scalar net declaration are nothing but the one bit declaration, one bit of information that we can observe from between the two devices. Whereas, for example, if it is a circuit 1 and if it is a circuit 2, okay, if it is a read, I am reading from circuit 1 to circuit 2, and here I am reading. I'm writing circuit 1 to circuit 2. So these can, the reading can be done with a 1 bit of information and writing can be done with the 1 bit. So I can say that this is a scalar quantity. Okay. And coming to the vector is nothing but a group of bits. So here from this circuit 1 and from circuit 2, my bits I am deriving is D of 0, D of 1, D of 2 and D of 3. So this is a combination of 3:0. So totally 4 bits I am using to transfer from one circuit to another circuit. So this 4 bits I am storing in a register called R. This is nothing but the vector net. So lastly, in the last, assign is a keyword, count and sum. You just count and sum, and so the comment here says that A and B vectors are added in C in. Coming to continuous assignment on vectors. So on vectors, how it is possible. So module, adder, A, B, C. So this is a basic representation. I am representing the module as a keyword. It is a basic operator, basic lexical token that we have discussed in the previous class, different lexical tokens. So it is one of the keyword called module, that is the starting of the statement. And adder is nothing but the gate, the circuit that you are making use of it. And A, B and sum are nothing but the port list, input and output ports. So here my input is 2:0 A comma B, and the output I observe is 3:0 sum. So here, as it is the adder, A and B are the two inputs, sum is the output, right? So input 2:0. Vector means more than 2 bits. So here my input would be 2:0, it is 3 bits, and my output would be 3:0, it is 4 bits. So sum I can observe is 4 and input is 2:0 A and B. And now coming to the fourth, assign. Assign is a keyword. I am assigning A plus B as sum, right? And then now I am displaying A is equals to percentile B, B is equals to percentile B and sum. So I am doing A, B together summing. And now I am ending my program with the end terminal. End terminal is also another keyword. Okay, to terminate the program. I am terminating my program with end module. So if you see here in the particular statement, you observe input, I mentioned declared input, declared output, and also I have declared the assign keyword with the mechanism. As it is an adder, I am going to sum up. Then the above code describes it is a 3-bit adder. So it is a 3-bit adder, 2:0, 2 plus 0, 1. 2 bits plus 1 output bit, totally 3 bits. So it's a 3-bit adder. The most significant of the sum is dedicated to carry in the above module, and it generates the following steps. So here in this, A is 100 and B is 111. If I sum up here, I'll get 1010. You all know the binary additions and the binary subtractions, isn't it? So 100 and 1, 1, 1. So here 0 plus 1, 1, 0 plus 1, 1 and 1 plus 1, 0, carry 1 and this carry bit as it is. So it is 1, 0, 1, 1. So my input is A is equals to, for example, 100 is nothing but 4, 1, 0, 0, 4 and B is 7. Totally I got the sum as 0, 1, 1 with the carry bit. Then the concatenation of vector and scalar net is also possible. The concatenation of both vector and the scalar is also possible. The same example for 3-bit adder using concatenation. I said that there's a possibility for the concatenation of both sum and the vector scales, vector nets. So we see with an example in the coming slide. So here is the example for the 3-bit adder using concatenation. So what is this? Module same adder A and B, A, B and sum. These are the port list consist of input port and output port. And my inputs are 2:0 AB and my outputs are 2:0 sum. Sum is a vector. So output carry is a scalar quantity. Okay, summing up, I'm summing up the bits, 2 bits or else 2 or more than 2 bits I'm summing. So it's a vector. So the carry that will come, I can get only one carry. It could be either 0 or 1. So that is a scalar. Next. So ascend is a keyword for this continuous statement. Carry sum A plus B. So ascend result to the concatenation of both scalar and vector. Why? Because here my scalar would be the output and my vector would be the sum. Scalar would be the carry. So here I'm concatenating both. So I'm displaying my thing. A, B, sum with the percentile B, percentile B, percentile B, both input, output and sum and carry, and I'm ending up with the end module. So here the output is observed like this. Same. So from this example, I can say that we can concatenate. The concatenation is possible for both vector and as well as the scalar net. Coming to the regular continuous assignment. So it follows the 2 major steps. One is declaring the net and the second one is writing a continuous assignment to the net, on the net. So here the below code, it shows or else it follows a regular continuous assignment. So in this regular continuous assignment, via out, that is the net out is declared. Okay, we have to declare, the second step is continuous assignment on the net, right? So via out, so net out is declared. Via is nothing but a keyword which is assigned for the net declaration, net continuous assignment statements. We are declaring a keyword called via. And for assign out A and B, assign is a keyword which is mentioned only for the common continuous assignment statement. So for this, assign is nothing but is declared for common continuous assignment statement, whereas via out is declared for the net continuous assignment statement. This is a difference you have to remember. And coming to the implicit continuous assignment, we can place a continuous assignment on net when it is declared. So here we can place a continuous assignment statement on net itself. Okay, whenever it is needed. The format will look like this. See, via out, which is equals to A and B. So in the previous, from this example, from these two, you can observe via out. Actually, it is a net declaration which is equals to assign out, that is A and B. So net declaration and assignment together. Together we have declared in a one format. So it's nothing but an implicit continuous assignment. Coming to implicit net declaration. So in Verilog, during the implicit net assignment, the LHS is declared. It will assign to RHS to the declared net. So we see in continuous assignment statement, there is an LHS bit followed with a delay, and there is an RHS followed with the output, right? So during the implicit assignment, LHS is already declared. Okay, declared with some delay, and it will assign to RHS net by using a keyword called assign. So, but if LHS is not defined, it will automatically create a net for the single name. So here one difference you have to observe is, if you are declaring the left hand side and the right hand side with the delays and with the output, there is a possibility, or else we can declare the assign can be to the RHS, the assignment can be directly given. In some cases, the LHS is not defined. For example, in that cases also you can say we can have that assurance that the creating of net is possible for the same single line. Though you are representing LHS, it's well and fine. If not, also we can create the net. So this is all about the implicit net declaration. So here we have a wire in two inputs, in 0 and in 1, and assign output. The assigned output is nothing but in 0, in 1. So this is XOR gate, isn't it? In 1 and in both inputs are in XOR. That means what here? The above example, it says that out is undeclared. Here you know, nowhere see here the out. But Verilog makes the implicit net declaration for out. So here if you see, we are nowhere declaring any out. Actually, we have to declare the out. But in this implicit net declaration, in this particular continuous assignment, even though we don't declare out also, the Verilog, it itself declares the out. Okay, this is one of the advantage, or else one of the key point to be remember. And coming to the delays, delays are nothing but there is a time gap between the input changes to the output changes. For example, my input, I am giving my input 0 at 1 nanosecond. So I should get my output exactly at 1 nanoseconds. But due to some mismatches or else due to some disturbances inside the circuit, it may go delay to 2 nanoseconds. So overall, with the difference of 2 nanoseconds, I am getting my output. So this is nothing but the delay. In the Verilog, we have several types of delays, and that delays we have discussed in the previous class also. So the delay value controls, what it controls, the time between the changes in the RHS operand. So this delay value, it controls the time at the output. For example, this is what the example I have given. My input I am giving it 10 nanoseconds, but I am observing my output at 20 nanoseconds. So overall delay I am observing here is 10 nanoseconds. So at the right hand side, at the output, at the expression, I can observe with how much of delay the output is observing. And also when the new value is assigned to LHS. So in this case also, when some new value we are assigning, instead of 3, sometimes abruptly I am assigning 4. So abruptly I am assigning 4, right? So in this case also there is a possibility of the delay output. So it is similar to specifying delays for gates. Obviously, in the gate level modeling, we see the delays. Okay, sometimes the delays would be high and sometimes the delays would be low, what we expected. Next, adding delays help in modeling the timing behavior in the simple circuits. So it helps us. The delay will helps us in modeling the timing behavior. So we can observe the delays. Obviously, in some cases the delay would be considered as an advantage in the modeling the time behavior in the simple circuits. Coming to regular assignment delay. What is this regular assignment delay? This delay we specify with the assign keyword. With keyword assign we specify, and the delay is applicable when the LHS is already defined. So in our expression, the LHS is already defined with some delay and RHS is with some expression. So already if the LHS is defined with some delay, the representation, the delay in changing the value already declared in net. That means what? When the delay is already declared in the left hand side of the continuous assignment statement, it means that already the net is also declared somewhere in the expression. So assign 10 nanoseconds of delay output, which is equals to in 1 or in 1 0 or in 1 1. So but that means what? The OR operator, the OR gate in 1 0 and in 1 1. For this output, there is a 10 nanoseconds of delay is observed. So if there is any change in the right hand side expression, it will be evaluated after 10 units of time. Okay. that will be assigned to LHS. So whatever the values that you are assigning, to the left hand side, with the same change you will observe at the right hand side with the 10 nanoseconds of delay. So at time t, if there is a change in one of the operand, then the expression is calculated at 10 plus t plus 10. So likewise, we have discussed previously, right? So my input is about 10. The output I am observed is 20. So with how much of difference that I am getting? T plus 10. Actual time is 10. But with 10 nanoseconds, I am observing the output. So the declaration would be 10 plus 10, t plus 10 units of time. With this much of delay, the output is observed. And it means that if both the input changes a value before 10 time units, the value of both repetition of t plus 10 are considered. Isn't it? So if both input 1 and input 2, or else input 0 or input 1, if the delay is at 10 nanoseconds, obviously the output, it gives 10 plus 10 nanoseconds of output. For example, if my input I'm giving 20 nanoseconds, so my output would be t plus 20 nanoseconds of delay will be observed in the output. Coming to the implicit continuous assignment delay. So what is this implicit continuous assignment? So we use this implicit, it specifies both the delay and assignment on net. That is, see, via 10 minutes of 10 nanoseconds of delay without both. That is implicit continuous assignment delay. This is how we represent via 10 nanoseconds directly output. That output is nothing but int 0 or int 1. So it's same as via assign same. So here this is the difference between the continuous assignment. A normal continuous assignment is simply we are assigning with 0, but with implicit continuous assignment we are assigning directly via 10 nanoseconds out in 0 or in 1. Both inputs of this is nothing but the AND gate. Next, coming to the net declaration delay. In this net declaration delay, this delay is associated with the net instead of the assignment. So here it is, the word says that net declaration delay. So it is associated only with the net but not instead of assignment. So the delay is added when the net is declared out without putting continuous assignment. So without the help of this assignment statement, only with the help of the net, the delay is added to the net. So here in this particular example, via with the delay 10 output, assign out is nothing but the output we are getting from the input, right? So out assign keyword out is equals to in. So this code has same effect as the following. So if you observe the difference, via out with 10 nanoseconds of delay, that I am assigning 10 nanoseconds of delay with the input with respect to the input. So this is just a declaration, syntax declaration for different kinds of continuous assignment statement. Okay, coming to the continuous assignment statement, implicit continuous assignment statement. Here it is used to assign the net value with some value is called explicit. So here you could see the two differences, implicit and the explicit. What is this implicit? See here in this particular example, he is telling via with a delay 1:0, A, which is equals to X and Y. This is implicit. Implicit is nothing but the net is declared. Verilog allows an assignment to be done when the net is declared. So here the net is declared already, such that we are calling this as an implicit. Whereas the explicit, it says that we are using, assign is used. The keyword assign is given to the net. So for this net, this is the net actually via 1:0 delay with the input A. So this net is given with respect to the assign A and output is X and Y. The important thing you have to remember between the difference between implicit and explicit is, for the implicit, assign keyword is used in place, assign keyword is used with respect to the net declaration. Whereas in implicit, directly via, that is a net declaration with a delay with respect to the input, nothing but the output. Okay, so here we have some example based on the combinational logic design. This circuit is it is a combinational logic design. It's a combination of some gates. So here you have AND gate, XOR gate, and NOR gate. So here we see how the implicit continuous statements we can make use with respect to this combinational logic circuit. So this requires, see here, we have a module combinational logic circuit, combo. The port list consists of input A, B, C, D, and the output O. So here, this is in the combinational logic circuits, the output is directly driven. Okay, output is directly, continuously it will driven to maintain the proper output. The inputs are continuously driven towards the output. This is a combinational logic circuit, right? So unlike sequential, in the sequential, if you observe, we use sequential circuits like flip-flops, latches and all, where the value is captured and stored. In the sequential, the values, the output, the input values are also output values. The values are taken and they can be stored in the registers. Whereas in combinational logic circuits, the output is continuously driven to the input bits are continuously driven to the output bit without any delays or without any stagnation. So, to assign statements fits the purpose well, because the output O is updated whenever input on the RHS changes. So here, this statement is talking about whenever you change the input, obviously the expressions will change. So LHS is, if you see the LHS consists of delay with assigned keyword, and RHS consists of the expression with the output. So whenever you are changing the input values, obviously the RHS expressions will change, okay, with the delays. For example, here, module combo, and this is a port list. Here, combo is nothing but the combinational circuits that I'm considering. Assign is a keyword. I'm assigning the output, which is equals to negation of A and B or C XOR D. So this is the operator. Already we have discussed different operators, logical operators, bitwise operators, shift operators, and so on. So C and D is nothing but the XOR operator. A and B is nothing but the AND operator. And in between, I am giving these two output to OR gate. So this is the OR operator. So, and I'm terminating my statements with the end module. If you observe this continuous, how the continuous, implicit continuous assignment takes place in the combinational circuit is, for example, in this example, you have AND gate, XOR gate and OR gate, right? So the output of AND gate is given as input to the OR gate. One of the input as OR gate, to OR gate. And the output of XOR gate given as one of the input to the OR gate. And from there on, the output is given to the inverter. Okay, NOT gate. And from there on, the output is observed. So here, you know AND gate 0 0 0 1 1 0 1 1. So AND gate is A dot B. A and B are the input. My output would be, if both are 0 0, it observes as 0 0 1 0 1 0 0 1 1 1. And you know, or XOR gate. What is this XOR gate? 0 0 0 1 1 0 1 1. When both are zeros, when both inputs A and B are 0, my output would be 0. When both inputs are 1, my output still remains 0. Okay, but in the different case, 0 when one of the input is 1, then my output will be observed at 1 1. Okay, and what is OR gate? 0 0 0 1 1 0 and 1 1. So 0 plus 0, A plus B, right? So 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. And 1 plus 1, 1. So this is what the truth tables for different gates. So here if you observe, I'm just considering 1 0 and 1 1, 1 0 and 1 1. My output goes as per this truth table. My output goes sometimes 0 and sometimes 1. Okay, and that 1 I'm giving as an input to the OR gate. And from here I'm giving that input as the OR gate. And from this OR gate, using the truth table, I'll be getting my outputs. And that output I'm giving to the NOT gate. So here, as per this, the delay, we can observe here clearly. So here you see A, B, C, D are the inputs. So here 0 nanoseconds, 20 nanoseconds, 40, 60, 80. This is the timing behavior of the circuit. We can easily identify and observe. So my A at 20 nanoseconds it's taking place, and at 60 nanoseconds it's falling down, and B same at 40 rising at 60. So the output O is equals to 1. I'll be getting I'll be getting output as 0 and 1. Okay, if it is 0, see my RHS, if it is 0, my RHS is false. If it is 1, my RHS will be true, isn't it? RHS becomes true when the output is 1, and the RHS becomes false when the output is 0. So here output OX from 0 to 10 nanoseconds. Here you can observe from 0 to 10 nanoseconds because input X during the same time. So here if you see 0 is equals to 1 when the expression is true. When the expression is true, we see it is rising up. It raised. And when 0 is equals to 0, it falls and it's constant. And then again if it is 1, again it raises, and then if it is 0, it falls down. But with a 10 nanoseconds of delay that we are observing here, the output is observed with a 10 nanoseconds of delay, and at the right hand side of the expression we can observe either if it is 0 or 1. If it is 0, the expressions would be false, and if it is 1, the expression would be true. So this is all about implicit continuous assignment, and we have some examples to be discussed, and that examples will be discussed in the coming sessions. So this is all about the implicit continuous assignment and different types in it. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.